Welcome to lecture number 10 in the Introduction to Lattice Boltzmann methods. Today we continue with multiple relaxation time method and go specifically to the cumulant method. So content of today is binomial transform, which we need to transform between raw and central moments. Then again we look at the or not again, but we look at the breakdown of Galilean invariance in the raw moment method, and then we come to cumulants. Okay, so in the last lecture, lecture number 9, we had the conclusion that the original MRT method, at least in 3 dimensions, has a problem with one of the fourth order moments, namely the moment M211, which has a spurious dependency on the moment M011, which we could remove if instead of using the classical MRT method from de Humière and Lallemande, use the weighted orthogonality. So the classical MRT method uses unweighted orthogonality between the moments. This leads to a spurious coupling, and we could remove this when instead of relaxing either this moment M211 directly or the unweighted orthogonalized moment, we could use the moment N21, small n21, which we defined as M211 minus theta M011, and this would then remove the coupling. Okay, so this was this observation, a singular observation, and this, of course, leads to at least two questions, namely whether there are any further dependencies that we have not yet seen, for example, in other moments, or even in the same moment. The second problem is, so these were raw moments, so in the frame of reference, in the resting frame of reference, and here's the question, does this frame of reference actually play any role? Okay, now this is what we are looking at. So there is this classical MRT method, that is the one from de Humière and Lallemande and Lou. Classical MRT. Classical MRT is based on raw moments. So raw moments are the ones taken in the material, and not in the material, in the lab frame of reference. So in the resting frame of reference, which we call the Eulerian frame, and the Eulerian frame is, of course, a fixed frame. So an alternative to this is to use moments not in the fixed frame, but in the frame that is moving with the material, so with the flow. And these then are using central moments. So we could write down a central moment MRT scheme. So, of course, this uses, instead of raw moments, this uses central moments. And that would be in a Lagrangian frame. so the frame attached to the material. So, how do these two things compare? We can write down the raw moments. As I said, Eulerian. So this is MABC is equal to the sum over I, J, and K. I by the power of A, J by the power of B, and K by the power of C. So this is what we have seen many times during this lecture. So the central moments so Lagrange Lagrangian. If I write Eulerian, I should also write Lagrangian. So we use to distinguish the two, we use for moments M, and for the central moments we use K, A, B, C. Now this is the same sum over I, J, and K. And now, instead of using these indices, these velocity indices, which are of course the velocity, the position in the velocity lattice, we use I minus, so I is the velocity index in x direction, so we subtract the macroscopic velocity ux, and because we have to normalize this to the lattice velocity, we divide it by the lattice velocity, which unfortunately is also called c. This is why I'm putting some serifs here in order to distinguish it from the other c. So this by the power of a, j, minus uy, divided by c with serifs, b, and this should use more space here. Yep. This multiplied by k minus u z divided by c by the power of c. So now this c is the c index here, and this times f, I, j, and k, and this c with the serifs, this is the velocity, the lattice velocity delta x by delta t, of course. So the velocities that we see here, ux, uy, and uz, are defined in the way that k100 is equal to k010, and this is equal to k001, and this is 0. So we choose ux, uy, uz in such a way that the first order central moments disappear. This is their definition. Okay, then it is possible to translate between raw and central moments using the binomial transform. So it's between different frames of reference. Now this would work like this. We have K, A, B, C. is equal to I equal to 0 okay, maybe I'm using different letters here because okay, I'm using alpha is equal to 0 till A. Beta is equal to 0 to B. And gamma is equal to 0. And this goes to C. And now it's A over alpha. So it's binomial coefficient A over alpha, B over beta, and C over gamma. And this goes into -1 by the power of A minus alpha plus B minus beta plus C minus gamma. And unfortunately, this equation is too long to fit into one line, so have to multiply all of this in the next line. M with the raw moments, M alpha, beta, and gamma into M100. So this is the first moment, M0 divided by M000 by the power of A minus alpha, M010 divided by M000 by the power of B minus beta, and M001 divided by M000, and this by the power of C minus gamma. So, and of course this binomial, as it is not a vector, the binomial is defined as, say, A over alpha is A factorial divided by alpha factorial times A minus alpha factorial. So that's the binomial. And this equation can be used to do the transformation of raw moments M alpha beta gamma to M to K ABC. So you see the central moment depends on all raw moments up to the order, up to the same order A, B, and C. Okay. Examples in 2D. So in 2D, we can leave one of them out, for example, the z direction. Yeah, and then we get, say, K20. K20, if we plug this into the equation, we get that this is M20 minus M10 squared by M00. And M10 is, of course, the velocity. The velocity in the momentum in x direction. So this, and M00 is the density. Therefore, we can rewrite this. So it's the velocity is the density square divided by the density. So it's, of course, M20 minus ux squared times rho. So very similarly, K11 is M11 minus ux uy times rho. So in that, we can also look at the equilibria. For example, we know from previous lectures that the equilibrium of the second order moment is ux squared plus theta times rho, and this is equivalent to the central moment, to the equilibrium of the central moment being theta times rho. And the equilibrium 1, 1, the moment m11, which is ux times uy times rho, is equivalent to the equilibrium of the central moment being 0. So the bottom line, so what we observe and what we also expect is that the central moment, where we basically eliminated the original velocity, becomes independent in its equilibrium from the velocity. The equilibrium of central moments is not a function of velocity, which makes sense because in the moving frame of reference, material frame of reference, the velocity is 0. Yeah? The velocity, so the velocity compared to the moving frame of reference is 0, so it cannot depend on the velocity because the velocity is 0 in that frame. So velocity has to be eliminated. Yeah, and now one principle of nature, it's called Galilean invariance. Means that the frame of reference should not influence the behavior of the method. Okay, let us see whether this is actually the case. And we test this by writing down the MRT equation in one frame of reference and see what they do in the other frame of reference. So let's assume we are relaxing the raw moments as we do in the standard MRT methods. So relaxation of raw moments, and then we express this in terms of central moments. So let's look at the moment m20, and we assume that there is, so this is the post-collision state, comes in the pre-collision state plus omega 20. So now we are not distinguishing between the usual, the shear viscosity and the bulk viscosity. They are both the same, so we're not splitting up the moment in two components. Yeah, we just look at the moment itself and say that this moment relaxes with the omega 20. And here comes the difference between the equilibrium and the pre-collision state. So this is how the MRT collision would take place. Now what we can do is we have a translation between the Ra moments and the central moments, so we can now write all these Ra moments in terms of central moments. So this is K20 asterisk. Now, as we saw, sorry for going back, but as we saw above, so this is M20 minus, so K20 is M20 minus UX squared times rho. Now we want to know what is M20, so we put the UX square rho to the other side and say this is now K20 minus, plus, we put it to the other side, so it's plus UX square rho. So this is what is on the left-hand side. And on the right-hand side, we have the pre-collision state. So it's now without star, K20, the velocity does not change. The velocity is conserved, so we assume there is no force. If there's a force, then it's not conserved, and that would be different, but we assume there is no force. So then we have plus UX square rho plus, and the same thing goes here on in the equilibrium state. Yeah, sorry, that must be K, equilibrium. So there's plus UX square rho minus K20 minus UX square rho. And what we discover is we are lucky with this one, because this here is canceling this here is canceling this here, and we'll end up with K20 after collision is the thing before collision, omega 20 K20 equilibrium minus K20. So we are lucky because this means that the relaxation of this moment, whether we do it in central moments or in Ra moments, doesn't matter. It's frame invariant. And this is also the reason why they came up with the MRT method in Ra moments in the first place, because, as you see, this is the way to go. You can relax the moments in any frame, and they always give you the same result. So, at least this is the case for the second order moments. So the same thing would be observed in K, of course K20 was the one that we had, K02 is the same thing, and also if you write it down for K11, you'll see that there's the same thing. Okay, so it doesn't matter whether we relax central moments or Ra moments in second order, because both of them give you the same result. So I would not be talking about this if there wasn't be a problem, and now we see it when we look at the third order moments. So let's see third order moments. So K21 can be written as M21 minus UX 2 times UX M11 minus UY M20. Yeah, as I told you, the binomial transform implies that the moment K21 is a function of all the Ra moments up to the order A equal to 1 and B equal A equal to 2 and B equal to 1. So they are appearing here, and we're still missing 2 UX uy rho. Okay, so why is this a problem? So previously, with the second order moment, there was a part that was directly related to the second order moment and another part that was conserved. Now here we have a different matter, because what is written here is not conserved during collision. So this here is just the velocity, so this would be conserved. Or let's say it is collision invariant, maybe it's even better. This is collision variant, so during collision this will change, and this is collision invariant. So in the additional term in the second order moments were all collision invariant, or there was only one term. Now let us translate this. So again, we have M11 is equal to K11 plus Ux Uy rho, and M20 is equal to K20 plus Ux square rho. And that basically means that M21 is equal to K21 plus Ux, so you plug these things in, and you see you get 2Ux K11 plus Uy K20, and all the remainder that come from these guys here, together with this guy above here, combine to plus Ux square Uy rho. So, okay, so this is now the second order. So the first order is the second order moments and one the third order moments, and now we can plug this into the above equation and see what is actually happening when we relax the raw moment. So we do the relaxation. In the Euler frame. Okay, so what's going to happen? So we have the moment M21 after collision is the moment M21 before collision, plus omega. Omega, now what do we have? Omega 21, so the omega of this particular moment. And here again we have the equilibrium minus the pre-collision state of that particular moment. Now we have to write a little bit, because we now have to replace all these raw moments with the central moment and see what is going to happen. So this is a lengthy thing, because they are not short stuff, but let's do it once in your life. So we replace M21, yeah, so this is the equation written up here. With this is plus 2Ux K11, and now this is a collision variant. So in this case, we are replacing the post-collision state. So the K11 is also the post-collision state here, right? Plus Uy comes K, the post-collision state, K20 post-collision state, plus Ux square Uy rho. So all of this is just a replacement of the left-hand side, M121 post-collision. So on the other side, we have to replace the pre-collision. So this is the same thing, it's just everything here is pre-collision, so without asterisk, 2Ux K11 without asterisk, plus Uy K20 without asterisk, plus ux square uy times rho. Okay, so this was, all of this was just the pre-collision state, and then we have to replace everything else. As I said, there's a lot to write here. So it's omega m to 1. Here comes the equilibrium. Now is everything the same, just equilibrium, 2, 1 equilibrium. 2 plus 2 ux k 1, 1 equilibrium plus uy k 2, 0 equilibrium plus ux square uy times rho. And now we still have to replace the pre-collision guy. Pre-collision guy is k minus k211 pre-collision minus ux times k11 pre-collision, and minus uy k21 pre-collision minus ux square uy rho. Okay, so now that's it. So a problem is these guys, because they depend on what the other collision does. However, we have seen that for these moments it doesn't matter whether we do the second order moments, and it doesn't matter whether we relax them in central moments or in Ra moments. So we'll not go back to the Ra moments, we just use the central moments. So we say that K20 asterisk is equal to K20 plus omega 20 K20 equilibrium minus K20 and K11 after collision is K11 before collision plus omega 11 K11 equilibrium minus K11. So this is something that we can now plug into the equation here above. And of course there are other things that we can take care of right now. For example, these guys here, the conserved guys here, they cancel out. For example, this guy cancels out with this guy, and these two guys here are canceling out. So with these simplifications and putting in the replacement that we have here, I'm not developing everything here, I'm just writing down okay, I probably write down everything. K21 asterisk. So after collision, here comes, so we replace this guy here. Is 2 okay, so when we do the replacement, say I'm doing a little bit of simplification before, yeah? So we have on the on the right hand side, we have these ux times K11 before collision, and the same guy comes when we plug in the K11 after collision in this position here. Yeah, so we can immediately see that they eliminate left side with right side, and everything that remains here will be the part here. So this is why I'm only now writing this part, otherwise it would become a little long. Yeah? So it's 2ux omega 1, 1, k 1, 1, equilibrium minus k 1, 1, plus uy omega 2, 1, 2, 0 into k 2, 0 equilibrium minus k 2, 0. And now I have to take into consideration that I've already implicitly eliminated all these other guys. So on the right-hand side, we'll just have k 2, 1. Everything else now has here been eliminated, and the rest that we get is related to omega 2, 1. Omega 2, 1. Here comes the equilibrium, k 2, 1 equilibrium minus k 2, 1 plus ux. So we'll put these things together, k 1, 1 equilibrium minus k 1, 1, and plus uy k 2, 0 equilibrium minus k 2, 0. Okay, now this is a bit simplified. Now we simplify this even more, because what we want to have, we want on the left-hand side only the k 2, 1. Let's do this and write that this is k 2, 1 after collision. So what is the third order moment after collision? And we see this can be written now as k 2, 1 plus omega 2, 1 k 2, 1 equilibrium minus k 2, 1. So I've taken this part out explicitly because this is the relaxation in the Lagrangian frame. That is what we like, but you see this equation here is a little longer, so there is something left, and the thing that is left comes with ux omega 2, 1 minus omega 1 minus omega 1, 1 into k 1, 1 equilibrium minus k 1, 1, and there's another term that is plus uy omega 2, 1 minus omega 2, 0 k 2, 0 equilibrium minus k 2, 0. And this is something that we don't like, because if you write down the collision operator in terms of the material frame of reference, the velocity of the frame of reference should not appear here. So this here is a violation of Galilean invariance. Okay, I write, because this is important, I write it down again. Maybe a little bit more accurate than the first time. So the Galilean invariance, any law of nature must be invariant with respect to the inertial, so this is kind of important, because the frame of reference must not be accelerated. The inertial frame of reference in which it is stated Now we have a problem, yeah? So we relax the moment 2, 1 in 2 different frames of reference, and we get a different result, and the result depends on the difference between the frame of reference, so the velocity with which the one frame of reference moves with respect to the other frame of reference. That's not okay. However, at the same time, we see that this can actually be repaired pretty easily, namely by choosing these relaxation rates in a particular way. As we see, if the relaxation rates are the same, this problem would disappear. And of course, we know a method where they are the same. This is the BGK method. In the BGK method, all the moments are relaxed with the same rate. And so the BGK method, this problem does not occur. So it's a problem of the MRT method specifically. Yeah? And it occurs for the first time. It also occurs at higher order moments, but it occurs for the first time at the third order moments. So they are not Galilean invariant. Unless we do BGK, namely that M21 is equal to, omega 21 is equal to omega 20 is equal to omega 1. If they are all the same, then this problem will disappear. Yeah? So BGK doesn't have this problem. And we were hoping that MRT is better than BGK, but here it is not. Now you could say, okay, so this is a numerical method and it's happening on a lattice. The lattice is finite, there's a discretization, so we'll never be able to develop on an Eulerian grid a method that is completely Galilean invariant. However, the point here is that in our calculation above, we did not make any use of the discretization. It was completely independent of the discretization. Yeah? So we did not assume any discretization. So this would happen for any discretization. So it's not an artifact of the discretization, but it is a problem with the concept itself. Okay, so what are the problems with problems of MRT? I mean, some of them. Okay, so the ghost moment, the third order moment is a ghost moment, yeah? So this is why the advocates of MRT would say it doesn't matter it's Galilean invariant or not, because it's a ghost moment, it does not appear in the Navier-Stokes equation, so we don't care, yeah? So, however, this thing is not, these things are not independent, so they depend on each other. So this is the one that, this is the one problem that we had last time in the lecture 9. They are not independent, even though they are orthogonal. Even though you went through all of the operations with the Gram-Schmidt operation and made it orthogonal, they are still dependent on each other, as we discussed last time. And what we had just now was that they are not only not independent of each other, but they are also not Galilean invariant. So there are actually a lot of problems with MRT. Interestingly, these things here are not a problem with BGK. Okay, but I'm not going to tell you that you should use BGK. I mean, there's a lot of people that you find online and everywhere else that will simply tell you, use BGK, and they may actually use the arguments that I've presented here to defend their position, but this is clearly not my position. The problem here is with BGK you have only one single relaxation time. And this, in the end of the day, this makes it very unstable and difficult to control. So, in fact, you can solve all the problems that we have with MRT in another way by just using different quantities from moments. So the problem is not in general that MRT doesn't work. The problem is that these moments are not the right variables to use in the MRT methods. So they are maybe not the best basis for MRT. And this is the reason why a different MRT method has been advised, and this is the cumulant method. Okay, so we have not talked about what cumulants are, but we'll now think about what our variables should actually, what do we demand from our variables, yeah? So we have these observable variables in the MRT method that are the moments. Now we have seen that they have problems with independence between each other, and they have problems with Galilean invariance. Now we are looking for different variables that don't have this problem. So, first of all, the variables we are talking about they should be independent. They should be independent from each other, because otherwise, I mean, if we want to do MRT, otherwise their relaxation would be coupled. Or is coupled. Okay, think about this. So there's a correlation between two variables. They are not independent. When they are not independent, then the one variable follows the other variable. If one variable follows the other variable, then at the end of the day, they must also evolve with the same time scale. Yeah. So if variable A is relaxing with time scale with a time tau, and the variable B is following this variable, then asymptotically, at least, variable B has to evolve on the same time scale. However, in MRT, the basis of MRT is the assumption that two things evolve in different timescales. So this implicitly requires that these things are uncorrelated, so that one variable does not automatically follow the other variable. Yeah, and this is what we actually mean with independence. So because this is the main problem in MRT. Because what they do in MRT, they also by using this orthogonalization, they also want to make variables independent of each other, but they have not discussed what they mean by independence. And this is the crucial point here. So what are independent random variables? So we're talking about random variables, yeah, because the distribution function is a statistic. Yeah, so there is a probability density function of finding a particle in a certain state. Yeah, so it is the velocity of a particle is a random variable. And its contribution to temperature and so on, this is all random variables. So now we here define independence like this, that if you know anything on one of the variables, so you have knowledge on the state of a variable, call it x. So there's not a position. Yeah, this is just a random variable. And this implies no knowledge on the state of y. Then the two are independent of each other. Yeah? So no knowledge means no knowledge on the probability. So for example, if I see you and you have black hair and you may have, say, a sister, then by knowing you, I know that the probability that your sister also has black hair is high, even though your sister may have blonde hair. Yeah? But still, the fact that you have black hair influences the probability that your sister has black hair too, even though she may not have black hair, but the probability is influenced. The variables would be independent of each other only if there is not even in a correlation between the probabilities. Only then would it be independent. Yeah? So for example, if you have a partner, yeah, say, so somebody that is not related to you, or your neighbor, yeah. So say, okay, your neighbor next door, yeah. And if I know your hair color, then I know nothing about the hair color of your neighbor next door. Maybe there's also some sort of correlation between this, but in general, you hopefully get the point. Okay, now we have to design variables that have this property, that they are independent of each other. And for this, we recall our moment generating function. That we had as f. So f is the Fourier transform of the moment so we have the Fourier transform. Okay, it's actually the Laplace transform. It has the same meaning, it's just a little bit differently written. So we have the Fourier, the Laplace transform of the the velocity distribution function, yeah, by the power of xi times. So xi is the velocity, and capital Xi is the Fourier transformed velocity, and this integrated over xi. And notice that from a perspective of the Laplace transform, though there's a different sign here, this different sign than in the standard transform. Yeah, so otherwise we would have e by the power of minus xi times xi. So, and this thing here is a function of the moments. So now what we did is we turned the probability density in the velocity space into a frequency space, and it's still a probability distribution. So we now have a probability distribution. This is the capital F. So the probability distribution now in frequency space, velocity frequency space. It's difficult to imagine what this is, so it's the Fourier transform of the velocity. So what makes statistical variables independent of each other? Same question as before. When would they be independent? So mathematically, we define statistical independence by saying that their joint probability distribution, so finding x in state A and y in state B is the product of finding x in state A and y in state B. That would be the case if they are independent of each other. That means that the distribution can be factorized. And this means there is no correlation between the two. So, which means that the joint distribution, that's a function of m1 till mn. So all the moments, so this distribution function, okay, all the moments, say all the variables, yeah? All the variables are in here, or f, say, yeah, all the variables, for example, we can write f in terms of moments, obviously, yeah? So now this should be a product of individual distribution functions, each of them depending only on one variable, namely ci. And now we say that if ci and say another of them, cj, if they are independent, meaning there's no correlation, their joint probability distribution factor. Okay, now we are going to use this property that the probability distribution function has to factor in terms of these new variables Ci as a means to define these variables. Yeah? So we use their property to actually derive what these variables are. And before we do this, we just look at how moments were originally defined. So the moments come from the moment generating function MABC is equal to this derivatives in Xi A upsilon, this is not a gamma, it's an upsilon, B, Z, and C. So this is now a different C. This is a small C here. I'm running out of letters over Xi. And this in the case of Xi equal to 0. So again, I remind you that Xi vector has the components now written Xi without vector upsilon and capital theta. So we can rewrite this stuff in another way, that this distribution function can actually be written as the sum over A, B, and C going to infinity, starting from 0 and going to infinity, over Xi by the power of A, upsilon by the power of B, and theta by the power of C, divided by A factorial, B factorial, and C factorial into MABC. Because what we do by this transformation is just writing the distribution, developing the distribution in a series expansion. Yeah. So the distribution is developed from a series of the moments. Yeah. Or the moments are actually the coefficients of a series expansion of the distribution. So what problem do we have here is that that these things here do not factor. If we want them to factor, we have to do something else. So for independent variables, we call these independent variables Ci. There is f of Xi must be a product from I equal to 0 to infinity over f I Ci. So we have to be able to write this as a product. So if this is a product, what we can do is we can take the logarithm of the moment generating function f of Xi and see that we can now, when we take the logarithm of a product, we get the sum, right? So we get the sum over I from 0 to infinity over the logarithm of fi from Ci. Okay, so now the problem we are facing is that with the moments, the moments are not independent because they are defined by a sum, where independent variables would be defined by a product. So since this is difficult, we see that we can rewrite the product in terms of a sum if the only thing that we have to do is, instead of using the moment generating function, so the Laplace transform of the distribution function, instead of this, we only need to take the logarithm of the moment generating function. So this then means we can rewrite this above equation, or not rewriting, but taking a different definition in our, say, expansion. So we expand not f, but we expand the logarithm of f and say, now this is a sum over a, b, and c, from 0 to infinity, over, so now we write everything the same way, set over by the power of c, a factorial, b factorial, c factorial, and now we just call these function not moments, but we call them c, a, b, and c, which is, of course, equivalent to saying that c, a, b, c is equal to these derivatives, c, a, epsilon, b, etc., c, of the logarithm. So the only thing that we did in comparison to the moments is we plug in the logarithm here. And now we evaluate all of this again at c equal to 0. So, and these things are called cumulants. So, if instead of using moments, we use cumulants in the MRT method, we expect that we have solved the independence problem. So we have now independent variables, and as a consequence of this independence, we also automatically get Galilean invariance. Okay, we'll go to prove this in a minute. Okay, so this is our expectation. Now the problem with all of this is that it's not so clear how to actually compute cumulants. So how do we do this? Computation of cumulants. So the first book on cumulants that I read was from Gardiner, and there was this funny statement just saying that there is no easy way to compute cumulants. It's very difficult to compute cumulants directly from the definition, but what we can do is we can compute cumulants from moments, and the way we can do this becomes hopefully clear in a minute. So let's say we are interested in the cumulant C001, which, going by definition, would be the derivative in the capital zeta direction of the logarithm of f, and this evaluated at c equal to 0. Okay, Now, instead of doing this directly, what we can do is applying the chain rule. And the chain rule, so the chain rule on logarithm of f, and f is a function of zeta. So then this means applying the chain rule will give us a 1 over f that comes from the logarithm times a d set f, and all of this still being evaluated at c equal to 0. Now, after applying the chain rule, we have eliminated the logarithm, and what we are left with is a derivative of f. And the derivative of f is the definition of the moment. Yeah? So what we discovered is, even though the direct computation of cumulants is difficult, by applying the chain rule we can obtain an equation that gives us the cumulant in terms of moments. So, and now if we evaluate this, so f, so we take the zero derivative of f. The zero derivative, this is the zero moment. So up, down here, we have the zero moment, m0, 0, 0, and this is, on the other side, we have the first order moment, m0, 0, 1, and this is momentum divided by density, and so it's velocity. Okay? So velocity is interesting because this is an... so moments, if they are not normalized, and we did not normalize our moments are extensive quantities, yeah? So they depend on the size of the system. Here we see the first order moment already is an intensive quantity, this is the velocity, and this is true for all the other moments too, as we'll see. So say we take the C002, what is going to happen? So this would be the second derivative of the logarithm of f evaluated at c equal to 0. So again, we apply the chain rule and do this transformation. What we obtain is minus d set f. So we have to apply the chain rule twice here. So this is what we get, and then we are left with a derivative of d set, the second derivative of f, and this again divided by f. By the way, if you find this difficult, you can use a computer algebra system, Maple or Mathematica, to do this derivatives for you. So the chain rule of the logarithm here. So the first thing that we see here, this is the square of the first derivative, so it's first moment. Yeah, so this will end up with being u set times rho square. Here we have a zero order moment, so this will be rho, and because it's square is square, what is left of this will simply be u set square. And this here is the second moment, so it's plus m002, and divided by f, zero moment f m00. So now if you do this for the other second order moments too, and you know that m002 equilibrium is u z square plus theta and this times rho, and you plug all of this in, and you see that, and you do okay, I made a mistake here. 3 times, okay. I have a small mistake in my lecture notes, I believe. Otherwise, if not, then I make a mistake now. So if you take these two, all of these cumulants together, what we'll end up with is 3 times theta. 3 times theta, and so there's no velocity or anything else in it, also not the density, and this simply is the temperature. Theta is the temperature. So now it's pretty interesting. So the first cumulants are the velocities. So the trace, the sum of the diagonal terms in the what is it, tensor of the second order moments, cumulants, they are the temperature. Okay, and this is pretty interesting, because we made a completely abstract mathematical concept, saying we are looking for variables that are independent, that are uncorrelated to each other. That's all that we required. And what pops out of this is stuff that is known to mankind like forever. For example, if you talk about moments, we are talking about momentum and energy. And actually, momentum and energy are things that are difficult to observe. So this is what is momentum? So why does something that is heavy has intrinsically more momentum than something that is light? These cumulants are things that are really easy to understand in nature. This is the velocity of a thing or the temperature of a thing. This is quite interesting. And now what else do we have other than velocity and temperature? You could say rather nothing. And in fact, what we observe, if we go further and further, is that the equilibrium of all the other, or all the higher, higher than second and the first and second, all of them are zero. Okay, so we don't have any other thing, at least not in equilibrium. Okay, let's have a comparison between cumulants and central moments. Cumulants in So what we are going to do is we change the frame of reference inside the Fourier or the Laplace transform. And the nice thing is that the Laplace transform allows us to do this pretty easily by using the translation rule. The translational rule is the same for the Fourier and the Laplace transform. This is also the reason why I'm always confusing the two. So if we are an Euler frame and we have F here, then we can write this in a Lagrange frame as a different F times e by the power of u times xi. Yeah, this is the translation here. We have to take into consideration that the sign convention is here opposite to the one, the sign convention of the Laplace transform that we are using is opposite to the standard Fourier transform, which is kind of annoying, but this is the way it is. So it's actually more like an inverse Fourier transform. So let's say we compute C, A, B, C, so this is small c, according to their definition from the moment generating function. So what we have to do is we take the logarithm of now the transformed, see, this is not what I wanted to write, of the transformed moment generating function that comes with e by the power of u times xi, and we evaluate the entire thing with at the position xi equals to 0. By the way, this is something that I believe could be confusing. Yeah, so the evaluation is at xi equal to 0. So what is very important when you evaluate this is that you do the derivative, and after taking the derivative, then you plug in xi equal to 0. Obviously, if you would plug xi equal to 0 before taking the derivative, all the derivatives would be 0, right? So that's the right, you have to take the right order of the operations. Yeah, so first derivative, you do the derivatives, and after the derivatives, you plug in the xi equal to 0. So because there is a logarithm and there is a product of two terms, we can use the logarithm to take this guy here out, and then, assuming that the logarithm is the natural logarithm, we can actually eliminate the logarithm against the exponential function, and this will give us this thing here. So we'll have u times xi, so this is what's left, plus the logarithm of f, the new function. Okay, now remember that because f with the snake, or the tilde, is in the moving frame of reference, by definition, in the material frame of reference, by definition, it does not have any velocity. So the first order moments of this would be 0. Yeah? So, but the cumulants would still be non-zero because they have here this part here. Now, this f tilde is completely independent of velocity because it's in the moving frame of reference, taken in the moving frame of reference. And from this term here will only generate a first moment and no further moments. So only the first cumulant depends on the velocity, and all the other cumulants in the hierarchy do not depend on velocity. And now this is obviously independent on which Euler frame we are actually using. So this here is intrinsically Galilean invariant because all but the order 1 cumulants, which are invariant under collision, they are frame independent, and this is what we want. So we are automatically Galilean invariant if we use cumulants. Cumulants are all frame independent. Okay, now from an efficiency point of view, it is better to write, to do the transformation between the moments and the cumulants in terms of central moments than in raw moments. So because we have to compute them from some moments. So it's writing cumulants in terms of central moments is more efficient than in terms of raw moments. So the reason is pretty simple. Let's write the moment, the cumulant C002 in terms of raw moments. So this will look like this, M200 on M2. So, okay, so this is this moment, and if we write this in terms of, because cumulants are independent on the frame of reference, so we can simply use the same equation to write it in terms of central moments. So it's simply exactly the same. So the only difference being that in central moments, by definition, these guys, so the first order central moments, they're all zero. So it's more efficient to write cumulants in terms of central moments, because whenever a central moment comes in first order, they will simply disappear. Yeah? So this will simply give you K002 by K000. Yeah? And for higher moments, this will become even more important. So the last thing we do now is to see whether cumulants also solve the problem that we had last time with the independence. This is what we designed them for. Let's test this. So in lecture 9, we had this problem of the MRT method with the moment specifically M211. If you are not aware of this problem and you're using some MRT with D3Q19 or D3Q15, then you simply don't have this problem because your method does not have enough degrees of freedom, which in this case is a good thing because your method does not produce this spurious viscosity, but on the other hand, due to the lack of this degrees of freedom, your method is not isotropic enough and will not give you good simulation results in general. So, on the D3Q27 lattice, which is the one that you should use, you have this problem. And the observation, let's say empirical observation, is that we could only remove this either what we had as either overdamping or instability. Both is bad. So we could not, what I'm writing, could not be avoided unless we change the moment to this N211, which we had as N211 minus theta M011. Okay, now what happens if we do not relax the moments, but instead we relax the cumulant? So for this, we first have to see what is actually the cumulant C11. So this would be K1, K11 divided by rho minus K200 times K011 plus 2K110 plus K101, and this goes over 1 divided by rho square. So actually this rho square here would be K000, which is rho. Okay, the problem that we observed was in our diffusive scaling at second order. Now we look at the same order here. So for this, we do an expansion of the cumulant. So we look at the cumulants to second order, meaning we have also the moments expanded to second order. So this here would be rho to the 0 order, minus, now we have to expand the products here. And now it's important to know that since these are all even order moments, they only contain even orders in the diffusive scaling. So because they have only even orders, there will be no combined term. Let's just write one of them down. So here would be the sum of, or the product of them needs to be of second order. So the sum of these orders have to be 2. Now, in principle, there could be a case where you have K200 to first order times K011 to first order. This would also be a sum of 2. However, because they are both even moments, they do not have odd orders. So this here does not exist. So I'm not going on writing this. However, something else exists, namely K200 to 0th order times K011 to second order. Yeah, and the other term also exists. So this is 2 times K110 to second order times K101 to 0 order plus 2 times K110 to 0 order and K101 0, 1 to second order. And all of this divided by rho to 0 order square. Now we know that these guys to 0 order are 0, so they would just disappear. To the 0 order, K200 to 0 order is theta rho to 0 order. Now if we plug all of this in, what we're ending up with is K is C211 to second order is equal to K211 to second order divided by rho 0 minus theta K011 to second order divided by rho to 0 order. And this is at the order that the problem occurred, exactly the equation that we had before, in the moving frame of reference. So it is not only the same, it is not only removing this correlation in the static frame of reference, but it is also, first of all, it is making the moments independent, and it does so in any frame of reference. So it's also Galilean invariant, which the other version would not have been. So this means that now the cumulants actually succeed. Of course, this is also observed in simulations. So the cumulants remove the MRT problem. And this means we still have now, so unlike in BGK, we still have the free choice of all the relaxation rates, because everything here is independent of each other, so we can freely choose these rates if we use cumulants, but not if we use moments. Okay, and this is it for today's lecture. Thank you for attending.